Okay. Now see students here. Now this is the original third order system converted into second order system. 3 poles converted to 2 poles. Insignificant poles should be eliminated. But what happened? The system parameters gain and time constant will not disturb. Time constant is same but gain is disturbed. That is the reason why this is the wrong answer. Okay. So without disturbing the gain and time constant, if you don't want to disturb the gain and time constant as a system parameter, so before you neglect the insignificant pole, convert it into time constant pole. Neglect insignificant but convert it into time constant. After that you eliminate that. Okay. Then I am converting into time constant form and eliminate. Then see here, what is the approximated transfer function now? Now the approximated transfer function, this 5 is also cancelled. Now which is nothing but 1 divided by s square plus 2s plus 2. Now see here, now this is the second order system. Now the original time constant is same, minus 1 by minus 1 second, because we are not disturb the dominant pole. If you are not disturb the dominant pole, time constant will never change. Now the system gain k. What is the system gain k? Limit s tends to 0 into transfer function, which is nothing but 1 by 2. Right? So now see here, now the time constant and system gain will be same as that of the original time constant and gain. That is the reason why this is the correct answer and this is the wrong answer. This is the wrong and this is correct. Okay. So you converted any higher order system into lower order system. Now by converting higher order to lower order, insignificant pole is eliminated. Before you eliminate the insignificant pole, convert it into time constant form such that the system parameters will not be disturbed, will not be changed, will be remain same, such that the system behavior will not be disturbed. Okay. So without disturbing the system parameter, will convert it higher order to lower order. Okay. Note down this. Okay. Now students, now you just see the time domain analysis of the second order system, include transient state analysis as well as steady state analysis and all the time domain specifications. Okay. Now in the same manner, now we just finish it time domain analysis. Now here I just find frequency domain specifications. Frequency domain specifications. Frequency domain specifications of a same second order system. Okay, such that we will finish this total. The frequency domain specifications of second order system. Right? Now, what is the time domain specification? Peak time, rise time, delay time, settling time, peak overshoot. Like that in the frequency domain specifications are also available. We will see. Now, we will see the practical second order system also. Now, this is a practical second order system, which is a combination of the practical elements. Now, this is V naught of t. Now, this is Vi of t. Then, if you find the transfer function, we already find this one in the transfer function analysis. What is the transfer function? Then if you find the transfer function, Laplace transformation of V naught of t is V naught of s. Laplace transformation of Vi of t is Vi of s. Laplace transformation of R is R. Laplace transformation of L is Ls. Laplace transformation of C is 1 by Sc. You already find the transfer function. Voltage across this resistance. Now output by input is the transfer function. That resistance by the total resistance you already simplified, 1 by LCS square plus RCS plus 1. This is the transfer function which we already do the same problem in the transfer function analysis. Now this I can take it. Okay. Now this is the practical transfer function of order 2. This is the second order transfer function. This is the practical second order system which is existing. Now V naught of S by Vi of S is the transfer function. Can I write like this? Now this is nothing but in the denominator I take LC as a common. So if I take LC as a common, this is 1 by LC. Now this is S square plus R by L into S plus 1 by LC. This is the second order system. And what is the standard second order system? The standard second order system, if you take it, now this is omega n square by S square plus 2 zeta omega n into S plus omega n square. Okay, so you compare these two. If you compare these two, now the natural frequency of oscillations omega n equal to 1 by root LC radians per second, 1 by root LC radians per second, and 2 zeta omega n, 2 zeta omega n, which is equal to R by L. 2 zeta omega n equal to R by L. So 2 into zeta omega n equal to 1 by root L into root C. Now this is R by root L into root L I can write. This is root L cancel. So zeta, which is equal to R by 2 into root C by L. So this is the damping factor zeta. And this is the natural frequency of oscillations omega n. And students are having a doubt that, sir, how I can find delta, sir? What is zeta? How I can get a over-damped response? How I can get the critically damped response? How I can get the under-damped response for different zeta values? The different zeta value, how I can verify? Now, by changing the RLC components, then this zeta is there. If you take R equals 0, zeta equals 0, undamped. Now, choose R and LC values such that you can find a overdamped response, you want an underdamped response, or you want a critical damped response. Whatever the response you want, you can easily find. This is the practical second order system. Sometimes he is asking, now what is the RLC values and damping factor is this much, what is R? Damping factor and capacity is this much, what is CL? This is the practical second order system. Okay, now you first take down this. Now students, this is the way how practically the damping factor at zeta is varied by changing the RLC component. Now this zeta is varied. Now we'll see the frequency domain specifications of a second order system. Okay. Now this is the standard second order system. Then there is a big derivation here, but without derivation also we can see that. Okay. Now what is the transfer function? Now the transfer function, which is nothing but omega n square by S square plus 2 zeta omega n into S plus omega n square. So now first I want to take omega n square as a common here. Now this is the transfer function. Now which is nothing but omega n square, if I take it as a common, 1 plus 2 zeta omega n into S by omega n square plus S square by omega n square. Omega n square cancel after taking the common. And replace S equal to j omega. If you take d of j omega, 1 divided by 1 minus j omega square. J square means 1 minus omega square by omega n square and plus j, s plus, replace s with j. If you replace s with j, 2 zeta omega by omega n, because already omega n square is cancelled. Now this is replace s equal to j omega. Now for easy calculations, then what I am doing here is, for easy calculations, let us assume mu, which is equal to omega by omega n. Let us assume mu, which is equal to omega by omega n. Now what is t of j omega? Now t of j omega, which is equal to 1 divided by 1 minus omega by omega n is mu, 1 minus mu square plus j into 2 zeta omega by omega n is nothing but mu. Now I want the magnitude, okay. So because I want to write the magnitude versus frequency curve such that I can find the frequency response, frequency domain case specifications. Therefore, what is the magnitude? The magnitude of T of j omega, which is nothing but real part is available, imaginary part is 1 divided by square root of real part. This is the real part. 1 minus mu square is the real part whole square plus imaginary part square. Imaginary part square means 4 zeta square mu square. Okay. Now this is the magnitude. Okay. This is the magnitude and this is the magnitude curve. Magnitude versus frequency. Then if you use this one, I just replace magnitude of j omega, which is nothing but, if you write directly also not issue, 1 divided by square root of 1 minus omega square by omega n square again whole square plus 4 zeta square omega square by omega n square. Instead of this big derivation, instead of this big equation, that's why I just put mu, which is equal to omega by omega n. We can take it mu, then that is easy for us. Okay. Now anyway, now you just take this one first. Okay. Now we will see the frequency response first, and after that we will find the frequency domain characteristics. Now this is the magnitude of the second order system. Now with respect to frequency omega radians per second. Now when omega equal to 0, substitute when omega equal to 0, this is 0, this is 0, 1. So when omega equal to 0, then this magnitude is some 1. But as frequencies changes, omega is changes, this magnitude is changes or not? Yes, as omega is changes, this magnitude is changes, and omega equal to infinity, something by infinity. Now this is nothing but 0. So because as frequency changes, omega is changes, then why I am writing like this? As frequency changes, omega is changes, at one particular frequency, then you can get the maximum magnitude. At one particular frequency, you can get the maximum magnitude. This particular frequency is called as the resonant frequency. This is the first time domain, frequency domain specification. And at that particular frequency where you can get the maximum magnitude, that is called as resonant peak MR. Now this is the frequency domain specifications. Now which is nothing but resonant frequency and resonant peak MR. This is the resonant frequency and this is the resonant peak. R for resonant frequency, resonant peak. Okay. Now we'll see how to find that. Now this is the, I can take it this as a reference. Okay. But what we are doing here, mu, which is nothing but omega by omega n. Okay. Now first we will see. So what is, I just give the definition first. What is omega? Resonant frequency. It is the frequency where you can get the maximum magnitude. Resonant frequency is the frequency where you can get the maximum magnitude. What is resonant peak? The magnitude at the resonant frequency. The maximum magnitude where you can get at the resonant frequency is called as resonant peak. So now I want first mu r, right? Omega r is nothing but mu r. Here I want omega, therefore you replace with mu r. Therefore can I write like this? Therefore then magnitude of T of j omega, now here you replace mu r, which is nothing but omega r by omega n. This I can take it as mu r, which is nothing but 1 divided by square root of 1 minus mu r square whole square plus 4 zeta square mu r square. Okay. Now where I replace omega, therefore this is mu r. Okay, right. So I want a resonant frequency. How you can get the maximum value of a function? Any response, any function, maximum value means differentiate, same. So if you differentiate this magnitude, response with respect to, this is, I take this is mu r, right? So with respect to mu r and equate to 0, you can get a mu r. That is the resonant frequency. So here I without doing the derivation I can write directly, but this derivation if you want you can do it. This is magnitude response, differentiate with mu r. This is mu r 1 by root x, x power minus 1 by 2. So minus 1 by 2 into x power minus 3 by 2. Again you do the derivation part of this and you can get a mu r square, which is equal to 1 minus 2 zeta square. You can get this answer. Okay. So you are, after doing this derivation part, you can get mu r square as this one. So from here I can write it as what is mu r square is this. What is mu r? Mu r is nothing but square root of 1 minus 2 zeta square. What is mu r? Mu r is nothing but omega r by omega n. Omega r by omega n, which is equal to square root of 1 minus 2 zeta square. What is omega r? Omega r is nothing but the resonant frequency, which is nothing but omega n into square root of 1 minus 2 zeta square radians per second. This is the resonant frequency. The frequency at which the maximum magnitude will occur is called as the resonant frequency. Now this is the resonant frequency. The frequency at which the maximum magnitude will occur is called as resonant frequency, and this is the derivation part. You just do the derivation of this, then you can get this answer. Now I can write directly. Okay, note down this. Okay. Now students, now see here. Now this is the resonant frequency. Now at this particular resonant frequency you can get the maximum magnitude, that is nothing but resonant peak. How you can get MR? Now the resonant peak is the maximum magnitude at resonant frequency. What is resonant frequency? Here you want to substitute omega is nothing but mu r. Just now we are substituting what is mu r square? 1 minus 2 zeta square. If you substitute directly this one, now which is nothing but if you substitute 1 divided by square root of 1 minus what is mu r square? Mu r square is nothing but this one, 1 minus 2 zeta square. Whole square plus 4 zeta square mu r square. What is mu r square? Mu r square is nothing but 1 minus 2 zeta square. So if you simplify this one, then you can get the resonant peak. Then you can get the resonant peak MR. You can get the resonant peak MR as 1 by 2 zeta into square root of 1 minus zeta square. This should be the resonant peak after simplification of this equation. Okay. So the resonant peak is at the resonant frequency. The maximum magnitude at resonant frequency is nothing but the resonant peak. Now here omega actually I can take as mu r. Mu r is nothing but square root of 1 minus 2 zeta square, which we already have a previous thing. So that you substitute directly, but mu r square, therefore this root is cancelled. Okay. So if you simplify that, this is the resonant peak and this is the resonant frequency. Okay. Next, first you take this one. Okay. Now this is the resonant frequency, resonant peak, and another frequency domain specification is cutoff frequency. So I want a cutoff frequency omega c, therefore again you replace. So this is mu equal to omega by omega n. So now I want omega c, therefore this is mu c. So T of j omega, which is equal to mu c, which is nothing but omega c by omega, which is nothing but 1 divided by square root of 1 minus omega c square whole square plus 4 zeta square mu c square, right? So this is omega c cutoff frequency. How to find cutoff frequency? What is the cutoff frequency? Now cutoff frequency is the frequency at which magnitude has a value of 1 by root 2, means 3 dB point. So cutoff frequency is the frequency, the magnitude is having a value of 1 by root 2. Now when the magnitude which is equal to a value of 1 by root 2, now that particular frequency is nothing but cutoff frequency. Cutoff frequency is the frequency at which magnitude is dropped down to 1 by root 2. So what is the derivation for this? So this is the magnitude. Now if this magnitude which is equal to 1 by root 2, now this magnitude which is equal to 1 by root 2, that particular frequency is omega c, that we call it as mu c. Okay. Now this is a square. I just give the analysis, you do it. Okay. Square both sides, root cancel, cross multiplication, and this equation if you simplify, you can get A mu c square plus B mu c plus some constant equal to 0. Okay? Or you can like x mu c square or y mu c plus z. Okay, this is better now, standard. A mu c square plus B mu c plus c equal to 0. Like that you can get one equation and find the roots. So if you find the roots, then you can get this mu c is positive and this mu c is to be negative. But this is the cutoff frequency. Don't take this one, because frequency is always positive. Okay, cutoff frequency is always positive. Like that, if you do the derivation, you can get mu c value as like this. So you get the mu c, which is equal to square root of 1 minus 2 zeta square plus again under root of 2 minus 4 zeta square plus 4 into zeta power 4. Right? Now this is mu c, but I want omega c. What is mu c? Mu c is nothing but omega c by omega n, which is equal to this one. Now what is omega c? Now the omega c, which is equal to omega n into square root of 1 minus 2 zeta square plus under root of 2 minus 4 zeta square plus 4 into zeta power 4. Now this is omega c, cutoff frequency. Now this is omega c, which is equal to omega n into under root of this one. Okay. Now this is the cutoff frequency, is another parameter of the another frequency domain specification of the second order system. Note down. Now these are the cutoff frequency, because frequency is always positive, that's why I don't take the negative side. Okay. So this is the cutoff frequency omega c, you can get it. See here, sir, how I can remember this big derivative, big formula? Easy way to remember. I will tell you that technique. Omega c equal to, in this omega c, first part is like a resonant frequency. What is the resonant frequency? I think that is easy to remember. 1 minus 2 zeta square. Am I not? In cutoff frequency, the first part is like easy to remembering. Okay, remember the first part is like a resonant frequency. Resonant frequency formula is already familiar and you can easily remember that. Okay. Now this first part is nothing but a resonant frequency, and what you are doing is, for the second part you should multiply it with the 2. The first part multiplied with 2 will be the second part. 2 into 1, 2, minus 2 into 2, 4. Understand or not? First part is like a resonant frequency. Second part, if you want, first part multiplied with 2. 2 into 1, 2. 2 into 2, 4. Only the last point, last parameter, last term you can remember. This is nothing but 4 delta power 4. This is only you should be remembered, then automatically you can easily get. This is the cutoff frequency. Okay. Now resonant frequency, resonant peak, cutoff frequency, and this is bandwidth. Next one is bandwidth. Okay. Now what is the bandwidth? The bandwidth is nothing but the range of frequencies which is already completed. Now what is the bandwidth? The bandwidth is nothing but the range of frequencies such that the magnitude is having a value of 1 by root 2. When the magnitude is having a value of 1 by root 2, 3 dB point. Now this is the bandwidth. The bandwidth which is nothing but highest frequency minus lowest frequency. The highest frequency is omega c minus the lowest frequency is 0. So the bandwidth is nothing but omega c itself. This is the bandwidth. So what is the bandwidth? The bandwidth which is nothing but fh minus fl, which is nothing but omega c minus 0, which is equal to omega c hedges. Now that omega c hedges is nothing but, which is nothing but omega c, which is nothing but omega n into, this is the bandwidth. Okay. Now this is the resonant frequency, resonant peak, cutoff frequency, bandwidth are the frequency domain specifications. Okay. Just take this one. I will do the comparison of the resonant frequency domain specifications and time domain specifications, just to give you the comparison. First you take this one. Okay. Now we just take a look of frequency domain versus time domain specification. Then you can get one clarity. Now this is the frequency domain specifications. Now what is the frequency domain specification? Resonant frequency omega r, which is equal to omega n into square root of 1 minus 2 zeta square. Now this is the time domain specifications. Now the time domain specification is the damped frequency of oscillations omega n into square root of 1 minus zeta square. Now one important point here. Now 1 minus zeta square is greater than 0. 1 is greater than zeta square. zeta square is less than 1, zeta is plus or minus less than 1, but don't take negative value, positive. And here 1 minus 2 zeta square is greater than 0, under root will become positive. 1 is greater than 2 zeta square. 2 zeta square is less than 1. Zeta is less than 1 by root 2. Now what we can understand? All the time domain specifications are valid only when the damping factor zeta is less than 1. All the frequency domain specifications are valid only when the zeta is less than 1 by root 2. Understand or not? All the time domain specifications are valid when zeta is less than 1. All the frequency domain specifications are valid when zeta is less than 1 by root 2. This was one important question. In a number of times this is asked in the previous competitive examinations. Okay. Now frequency domain specifications are valid when damping factor zeta less than 1 by root 2, and this time domain specifications are valid when zeta is less than 1 and greater than 0. Okay. This is the important point while doing the time domain calculations and frequency domain calculations. Take this one. Okay. Now these frequency domain specifications are valid when damping factor zeta is less than 1 by root 2, and time domain specifications are valid when zeta is less than 1. Therefore, now what is omega d? Now don't confuse, this is omega r. In the examination also you can have to identify. Resonant frequency means this formula. Damped frequency means this formula. And most of the students are confused. He is asking resonant frequency and you blindly do omega d. Is wrong. Now this is omega r, resonant frequency. Now the resonant peak which is equal to 1 by 2 zeta into square root of 1 minus zeta square. Now here a resonant peak, here this is peak time. What is peak time? Peak time which is equal to n pi by omega d seconds. This is frequency response, right? Now this is the resonant frequency, and here this is the cutoff frequency which is equal to omega n into square root of 1 minus 2 zeta square plus square root of 2 minus 4 zeta square plus 4 into zeta power 4, right? And bandwidth which is nothing but omega c hertz itself. Now here the rise time which is equal to pi minus theta by omega d seconds, and delay time which is nothing but 1 plus 0.7 zeta by omega n. This is the time domain specifications, and a peak overshoot which is equal to e power minus zeta n pi by square root of 1 minus zeta square. These are the few frequency domain specifications, and the settling time which is equal to 5 time constants for 0% error. So these are the list of time domain specifications versus frequency domain specifications. Now students, the frequency domain specifications are with respect to frequency for the same second order. This is for time domain specifications of which system? This is for the second order system. Okay. Now for a second order system, the time domain and frequency domain specifications. Now this is the second order system. Okay. This is totally I am talking about which system? Second order system. Second order system, frequency domain and time domain specifications. So in the examinations also you should be take care what he is asking. He is asking frequency domain specification or time domain specification. He is asking resonant frequency or he is asking resonant peak. He is asking resonant frequency or he is asking damped frequency of oscillation. Okay. Now all these are the time domain specifications which are valid when zeta is less than 1. All these are the frequency domain specifications which are valid when zeta is less than 1 by root 2. That is the difference. Okay. And the natural frequency domain response is the natural second order system is also a combination of RLC and L and C, two values or two storage elements are equal to 2. Okay. Now this is actually the total second chapter, which is time domain analysis. Okay, this is the total second chapter, which is the time domain analysis, which include the first order system and second order system, transient state analysis, steady state analysis, which is very important for the GATE examination point of view. Okay.